Today I'm going to talk about LeetCode question number 778, swim in rising water. So you're given an n by n integer matrix grid where each value grid ij represents the elevation at that point ij. Rain starts to fall. At time t, the depth of the water everywhere is t. You can swim from a square to another 4 directionally adjacent square, up, down, left, right, 4 directionally, if and only if the elevation of both squares individually are at most t. Okay, so for example, at time 0, we're stuck here. Can we move here at time 0? No, we can't, because it's not at most 0. And same thing here, we can't move to this grid here at time 1 because t should be at most 0. But if time is 1, if we're here and time is 1, then we can travel here. We still can't travel here yet because we can travel to grids at most 1. Okay, so that's basically what that means. You can swim infinite distances in 0 time. Of course, you must stay within the boundaries of the grid during your swim. Return the least time until you can reach the bottom right square, n-1, n-1, if you start at the top left square at 0, 0. Okay, so I think this is kind of a better illustrated example. So we're here, for example here, at time 0, we're here initially. Okay. And you want the least time we can reach the bottom right square, okay? So, for example, we can either go here and here, but in order to reach this square, t has to be equal to 3, okay? Because otherwise, if and only if the elevation of both squares individually are at most t, okay? Because we need t to be 3, okay, in order to travel to this most bottom right square. What if we start at 0 and this was like 12 and this was 11? T is not 3 in this case because we would need we need the least time, so we need t equals 11. We can go here where t is 12, okay, but 11 is smaller, so we choose this path instead. Okay, and why do we need t to be 11? Well, in order to travel from this grid to this spot here, we need time to be 11. Okay, if time is 0, we can't travel anymore. If time is 1, we still can't travel anywhere. 2, 3, 4, 5, etc. And then finally, once it's 11, we can travel here. And since t is already 11, we can simply travel here. Okay, do not need to wait for it to go back down to 3. Time doesn't go backwards. And since we're already at a maximum of 11, if we had like another grid here of like 10, we can also visit this guy here. But yeah. Okay, so that's kind of how it works. So basically, what we're looking for, let me just erase all this, is the path with the least maximum in order to reach the most bottom right square. Okay, the least maximum. In this case, the least maximum is 3, and with before with 11 and 12, the least maximum would be 11. Let's look at this example here. What would the least maximum be from here to here? Well, it would be 16, okay? Like this. Okay? We can't take any other way without having a maximum larger than 16, okay? If we try this, our maximum would be 24. If we tried to be clever here, our maximum would be 23. And etc. So the maximum we found in order to get here is 16. So how are we going to do this? Well, we can use a modified Dijkstra's algorithm using a priority queue. And Dijkstra's algorithm, what they use is a priority queue or a min heap. Okay, so how are we going to use this min heap? So I'll just draw that there. Initially, our min heap is going to have the value It's going to store value and our I position and our J position. So initially it's going to be, uppermost left here. So our val, if we were to take this second example, it would be 0, 0, 0. And then we look each of the 4 directions. This is out of bounds, so that doesn't count. This is out of bounds, so that doesn't count. So let's look at these two. And what we're going to store in them is our next potential position, and we're going to be a bit greedy about it. Okay, so we're going to take the smaller of our next directions here. So right now what we take is actually we're going to store both directions in our min heap. So one, I'm just going to put I and J, and then 24 I J. Okay, so we pop that from the min heap, and with the nature of the min heap is we pop smaller element, smaller value each time, which would be 1 in this case. So now we would travel to 1 here. Let me do that in different color. So this is our path here right now. Okay, and then from this guy, in the next iteration, we would pop this, and again we look bi-directionally. Okay, and then obviously we would put in both 23 I J and 2 I J. Okay, and then obviously we're gonna pop 2, and then this is our path so far, and etc. That's basically how we're gonna go. But one thing we have to keep in mind is, what if, say, we're here at 16, okay? We're here at 16. I'll draw this here. 16 I and J, okay? And we were to add the next 4 directions. By the way, we're going to keep track of visited position, so we don't accidentally backtrack and visit another position again. So we went from 5 to 16. And we now look at 16's other directions, which would be 15 and 20 here. Okay, so this would be popped, and then we would put 20 I J. Okay, and what about this 15? Do we put in 15 I J? No, what we do is take the maximum of this current value and the position we want, and the next cell we want to put in our heap. We take the max of 16 and 15, okay, instead of this. And same for every other one here. Everything else we put in our heap, okay, because we want the least maximum it will take to get to this bottom right square. Okay, least maximum, and we want to keep track that the maximum we found so far was 16. So that's why we pop in 16 into this, push in 16 into this heap rather than 15. Okay, so we're going to take the maximum values, because we want to keep track that 16 is the biggest so found in our trek to the bottom right square. Okay, so yeah, the time complexity of this will be, so it kind of be traversing through this matrix here, so, and it's an n by n matrix, so n squared, plus we need to take into account the heap operations of like popping from the heap, and of course those obviously take log, so log n squared. Okay, n squared, because potentially we could pretty much add every element into this heap, or so push in takes log, I mean. Okay, and with the nature of logarithms, what we could do is take that exponent and add it up here. And since we don't take constants in the time complexity, this would be O of n squared log n. So O of n squared log n. Okay, and that's how we're going to go about it. Okay, so now to code this up, so what I'm going to do is store our size of the grid. So n is going to be equal to length of grid, and this n will represent our row length and our column length, because remember this is an n by n matrix grid. Okay, and then what I'm going to do now is basically have a visited set. Okay, it's going to store all of my visited i's and j positions, so you don't actually go backwards. And then my heap, and then I'll heapify that heap. And then first thing I'm going to add to the heap is the index at 0, 0. So the upper leftmost index here. 0, 0, our starting position. And what this heap is going to store is a tuple of the value of that square, and I position and j position. So obviously what I'm going to push here is matrix at 0, 0, and then 0, I position 0 and j position 0. Okay, cool. And basically I'm going to add that to our visited to dot. And visited is going to store the I and j. Okay, so now we can kind of basically get started with our modified Dijkstra's. So while true, what I'm going to do is get the val and the I and the j and pop that from my heap. Okay, great. And if what we pop, so if I is equal to n minus 1 and j is equal to n minus 1, so basically if we're at the most bottom right square here, return val. Okay. Or else what we're going to do is check for directionally its cells and then add that to our heap and continue our trek. So it's going to be our up direction here. If I minus 1 greater than or equal to 0 and I minus 1 less than or equal to actually what I'm going to do here is do minus 1 just to make it easier, because this is 0 indexed. And rather do the 0 index operation here, I'll just do it up here at one spot. This is also equal to n and I minus 1 j not in visited. So what I'm going to do is heap q dot heap push into our heap here tuple, and the tuple is going to contain the maximum of our current value and the grid, the adjacent grid we're visiting. And j Okay. And I-1 and j. Okay. Let me check got my brackets right here. And yeah, looks good. So that's the up direction, and here's the down direction. So it's +1 because we're going down a row, and I represents the row. Okay. Now let's do our left direction, going -1 a column. So if j -1 greater than equals 0, just checking our bounds here, and -1 less than or equal to n, and j -1 not n base good. One thing I forgot to do is add whatever we add to the heap, we have to add to visited, so you don't accidentally visit it again. So we got add tuples I -1 and j. And it's I +1 and j. So here we're going to do is keep q dot heap push, and for a heap here, a tuple of the max of val, and what's upcoming in the next grid cell, so grid j -1 I and j -1, and they just say dot add I j -1, and that's a tuple. Okay, and similarly we're gonna, with the left direction, and we're gonna do the right direction. Okay, and yeah, that's pretty much it. Basically guaranteed an answer, so we'll have that there. And yeah. Okay, I'll go to dry run. No, it's not called matrix, it's called grid. Okay. And try again. Okay, and I'll try one more test case here. Cool, and I'll submit. Okay, great, thanks for watching.